Hey guys, this is Miss Watson here. Today we're going to be talking about section 11.3, probability of multiple events. Okay, so first thing we want to talk about is the concept of dependent versus independent. And we're going to do that by defining dependent. And that is the occurrence of one event affects the probability that another event will occur. So the occurrence, of one event affects the probability that another event will occur. So if this is true, then that means the events are dependent. So what you're really asking yourself is, does, sorry about that, let me rewrite that, does the first event have any impact on the outcome of the second event? Okay, so again, does the first event have any impact on the outcome of the second? So let's look at a couple examples here. It says, are the outcomes of each trial dependent or independent? So first example is you roll a number cube, then spin a spinner. So does it matter what you roll on the cube? Um, does that have any impact on what you spin on the spinner? The answer is no. So these would be independent. Okay, next example. You pick a card, and then you pick another card from a standard deck of cards. So you have 52 cards in front of you. You pick one card, you hold on to it, you pick another card. This is dependent. And this is because there's one less card to choose from on the second draw. So these are dependent events. Okay, so now go ahead and try the next one. The video is going to pause. Go ahead and try the next one. Okay, so you select a coin at random from your pocket. You look at it, you think, great. Now you replace the coin and select again. So this is super important right here. You replace the coin and select again. So you put it back in your pocket. Are your selections dependent or independent? Because you put the coin back in your pocket, this is now independent. Okay, and this is different from the card situation because the card situation, you didn't put the card back in the deck. Okay, it has to tell you you replace it. But this one, since you put the coin back in your pocket, you're starting with the same number of coins again. So what you picked on the first time has no impact on what you're going to pick on the second time. Okay, so why do we care? So first thing we're going to look at is probability of A and B. Okay, so we're going to look at A and B, and then we're going to look at A or B. So if A and B are independent events, then we use notation here. The probability of A and B occurring is equal to the probability of A times the probability of B. Okay, so you find the probability of each and you multiply them. Okay, and this is if they're independent. So here we go. Here's our first example. At a picnic, there are 10 diet drinks and 5 regular drinks. There are also 8 bags of fat free chips and 12 bags of regular chips. If you grab a drink and a bag of chips without looking, what is the probability you get a diet drink and fat free chips? So, what are we looking for? Probability you get a diet drink and fat free chips. So, what I'm going to do here is I'm going to call um, diet drink event A. And I'm going to call fat free chips event B. Okay. And so, using our formula, it says that probability of A and B, so getting both of these is equal to the probability of A times the probability of B. So let's break these down. Probability of event A, so getting a diet drink. So diet over total drinks. How many diets are there? There's 10. How many total drinks? 15. Okay, so we're going to put that over here, 10 over 15. Do the same thing for event B, so fat-free chips. We have fat-free over total chips. How many fat-free are there? There's 8. How many total chips? 8 plus 12, 20. So we're going to put that over here. Okay, then we're going to use our calculator to multiply these out. And we're going to get 4 over 15, which as a decimal is 0.267. So as a percent, it's 26.7%. And that's rounding to the 10th on the decimal. Okay. All right, go ahead and try the next one on your own. All right, here we go. So this one is using the same example, but now it's what is the probability of getting regular drink and regular chips? So we're going to use the same formula here. Probability of A and B is equal to probability of A times the probability of B. Okay, this time A is going to be regular drink. So let's call this A and let's call this B. Event A and event B. Okay, so regular drink this time. Well, there's 5 regular drinks over still a total of 15. And now regular chips, there's 12 over a total of still 20. Okay, hopefully you multiply that out and you get 1 over 5, which as a decimal is 0.2 and as a percentage is 20%. All right, let's keep moving. Now we want to talk about mutually exclusive events. Okay, what does it mean when 2 events are mutually exclusive? So, mutually exclusive events means 2 events, or they are 2 events that cannot happen at the same time. Oops. Okay, so let me get rid of that. 2 events are mutually exclusive if they cannot happen at the same time. And why do we care? Because the probability of A and B is equal to 0 if A and B are mutually exclusive. Okay, and that just kind of goes by the definition, right? If 2 events cannot happen at the same time, then the probability of them happening at the same time has to be 0. Okay, so let's look at a couple examples here. It says task 3, you roll a standard number cube. Are the events mutually exclusive? So you have 1 cube, can you roll a 2 and a 3? You cannot. So yes, mutually exclusive. Because you can't roll a 2 and a 3 at the same time. You only have 1 cube. Now, some of you might be thinking, because I get this every year, well, what if it lands on its side? What if it lands against something so it's like tilted? Okay, so we're talking here, right? A legitimate roll, a fair roll where it lands flat. If it lands flat, it can only land on one number. Okay. All right, part B. Rolling an even number and a multiple of 3. Are these events mutually exclusive? Right? This is not mutually exclusive. Right? Because it can happen at the same time. Okay, so here's an example. You could roll a 6. So 6 is both even and a multiple of 3. Okay, so we would say that these two events are not mutually exclusive. Okay, so why do we care? Because that plays a part when we do the or statements. So now we're looking at the probability of A or B occurring. All right, so here's our formula. Probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Okay, so this is definitely one that you should be writing down. I'll do it again. The probability of event A or event B occurring is equal to the probability of event A plus the probability of event B minus the probability of event A and B occurring. Now, here's the deal. If A and B are mutually exclusive, then it just looks like this. Probability of A or B is equal to the probability of A plus the probability of B. And that's because what we looked at above, if they're mutually exclusive, then this happens, right? If they're mutually exclusive, then the probability is 0. So that last term here would just be 0. So it would be probability of A plus probability of B minus 0. Okay? So let's look at a couple examples. So at your high school, a student can take one foreign language each term. Not necessarily true at OP, but let's pretend it is. Okay? About 37% of the students take Spanish. About 15% of the students take French. What is the probability that a student chosen at random is taking Spanish or French? So, right here, what are we solving for? Taking Spanish or French. So this is an or statement, right? So we want to start like this. Probability of, and I'll just call this SP for Spanish or FR for French, just so you can see the difference here, okay? So it's going to be the probability of Spanish or the probability of French. I'm sorry, that should be a plus right there. Minus the probability of Spanish and French. Okay, so now some of you guys must be thinking it already, and so I'll just go right to it. Is it possible? Are these mutually exclusive? They are. It cannot happen at the same time. Where do I see that? It says a student can take one foreign language each term, right? So these are mutually exclusive. Oops. Oh, having trouble here. Which means the probability of Spanish and French is just equal to 0. So we're going to plug 0 in there. Okay. What about the other two? The probability of Spanish is 37%, so 0.37. French is 15%, so 0 plus 1, 5, minus 0. Okay, so what do we get here? We add those two together. We put 0.52, so as a percentage, 52%. Okay, all right, let's try one more together. So it says, suppose you reach into a dish, the dish shown at the right, and select a token at random. What is the probability the token is round or green? Okay, so I'm going to do probability of round or green. So it's a probability of round plus the probability of green minus the probability of round and green. Okay. And you might be thinking, well, do I have to worry about that last one? Well, it turns out in this one you do, because it's not mutually exclusive. There are tokens that are round and green, so you have to take that into account. Okay. So first thing is, how many total tokens do we have in here? Count them up. You should get 9. Okay, so that's important to know. All right, so probability of round, count up the rounds. We have 1, 2, 3, 4, 5. So 5 over 9. How many greens do we have? 1, 2, 3. So 3 over 9. Less, how many round and green? 2. So 2 over 9. Okay, so again, you do have to take into account the and there because they're not mutually exclusive. You could have a round and a green. So do this, you're going to get 6 over 9, which reduces to 2 over 3, which as a decimal is 0.67, or as a percentage is 67%. Okay, go ahead and try the last one in your own. So now it says, same thing. You reach into the dish and select a token at random. What is the probability that the token is square or red? So square or red. So hopefully you did something like this. Probability of square or red is equal to the probability of square plus the probability of red less the probability of square and red. Okay, now we're using the same dish, so we know there's still 9 in total. So how many of the 9 are squares? We count them up, we get 3 over 9. How many of the tokens are red? 3 over 9 as well. And now how many are square and red? There is one that's square and red, so 1 over 9. Okay, work that out. You should get 5 over 9, which as a decimal is 0.56, and therefore as a percentage is 56%. All right, guys, that's all we have for today. Hopefully that made some sense and gives you some confidence as you approach the homework. Thanks.